Hello everyone, my name is Heizika. In the previous video, we have already implemented self-attention, positional embedding, and multi-head attention. And in the next videos, we are going to implement vision transformer, which is a concrete example of transformer which is used in computer vision. And I'm going to share the link of the paper in the description. And we can now we are going to look at the figure in the picture in the paper. And the first step is division. We divide the picture into three embedding. For example, uh, if the original shape of input image is 390, 3 means it has three channels, RGB channels, right? We are going to use channel first notation. And it has three channel, and the width and height is both 90. And we divide it into 9 patches. The left up one, and the 8 left ones. So we divide eight 9 patches, and each patch is of the shape of 3 30 30. 3 means the number of channel which doesn't change, and the height is 30, the width is 30. Now we are going to convert each patches into an embedding, and the method we are going to use is convolutional layer. Uh, for example, if you use a kernel size of 30, and the stride is also 30, so now in the 2D convolution, the number of kernels you used is equals to the output channels. So for example, if you use 10 kernels to do convolution on this patch, now the output channel will be 10. So and the width and height will be 1 because the kernel size is 30 to 30. Now the reason why we are doing this because we want to convert each patch into a one-dimensional embedding, because in the transformer each embedding is one-dimensional. And now we add positional embedding to it, and this is extra learnable embedding, and we send it to transformer encoder. The major part is multi-head attention and MLP, which is just linear layers, and actually it has 10 outputs because we have 9 batches and an extra embedding. So we have 10 outputs. We just ignore all this. We just throw them away, this 9 outputs, and we just use this outputs. This output, because it has already incorporated information from the other 9 batches, and now we send it to MLP head, and we got the result of classification. So the architecture is not difficult. Now we are going to, but I think I need to use several, maybe 3 or 4 videos to implement a vision transformer. And in this video, I'm going to implement patch embedding, which is this part. We convert the whole image into 9 patches, with aka 9 embeddings. So the number of patches may vary. So it doesn't matter. The principle is exactly the same. So we are going to And the parameters we are sending in is the image size. We are going to set the divide value of image size to 224, and the patch size means the height and width of each patch. In this example, the patch size is 30, and the grid size is 3 because we divide 9 grids, and each grid and aka each patch is of the shape of 30 times 30. So patch size in this I'm going to set divide value of patch size to 16. So each patch has 3 channels, and the height and the width are both 16. In channel equals 3 because we have RGB channels, and I'm going to use a notation we used in the previous video. We set the length of each embedding. We call it dA, which is the length of each embedding. We want to set it to 768. And yes, I think that's we can use norm layer to normalize each embedding, to normalize those embeddings. Okay. The height and the width, right? A patch is just a part of an of the whole image. So and then now we need to set divided by patch size. Patches we have. And in this case, we have 14 times 14 patches, and each patches is 3 times 16 times 16. So and how we are going to convert a patch to an embedding? We are going to use convolution. number of channel in channels equals number of the in channels, and kernel size equals to batch size, because we want to the output height and width to be 1. Stride also equals patch size. So actually, we are going to convert a 3-dimensional patch to a one-dimensional embedding. So it's 3, and in each case 16. We're going to set the output channel equals dA, which is the length of each embedding. So I think it's also always remember that in PyTorch, they use the channel first notation. So the first dimension means the number of channel. The reason why the output width and height is 1, I think if you are familiar with convolution, you can easily understand why it is. But if you are not familiar with convolution, you can watch other tutorials. So and the last thing, the only thing we have not done yet is the normalization. We can it's not necessary, but we are going to implement. If we haven't sent norm layer, we just use dot identity, which actually don't do anything. So now we need to create a forward function and x. So first we need to be clear of the shape of x. The first dimension is batch size, and batch size, number of channel, height, and width. So x has 4 dimensions, right? And we need to make sure that height, because you can say that we have already, if we send image size, we need to make sure that the image match that image size. So we need to add a word, a search sentence. And now we are going to convert each patch into an embedding. So we use convolutional manipulation on the image, and we send X in. Look at here that because for each patch, it's the output y and hat is 1. Because we have 14 times 14 patches, so this becomes 14 and 14. And actually, we want to put dA to the last dimension. So actually, we need to flatten the last 2 dimension and transpose. I'm going to explain it. The first, the output, the shape of x. After we do self-dot conversion, x, the shape of x becomes to because we have 14 times 14 patches. So now we have 14 times 14 embeddings, and each embedding has 768 numbers. I think if you have already in the previous video, the custom we use is we set the dA to the last dimension and the number of embedding before it. So we use it to flatten the this dimension. So it becomes to 14 times 14 equals 196. So I'm sorry, I missed a batch size. I'm going to set batch size to 1, and so it doesn't matter. So we flatten this dimension, so it becomes this, and we transpose this 2 dimensions, so it becomes 2. Yes, this is a notation we used in the previous video. The first dimension is batch size. The second dimension is number of embedding. The last dimension is length of each embedding. So now we can send it to the transformer block, right? And you can do the normalization, which is not necessary. Yeah, I think that's all about. Yeah, I think all about the patch embedding, and we can test it. For example, if we want to equals touch.range 3 channels, width, height, and width. Embeddings. First, we need to instantialize a class. So we need to send in the image size and I think we can all use the default value. If you send an image which is 300 to 300, you can send in the image size explicitly. But if your image is 224 times 224, you don't need to send in. You can use the default value. I think yeah, we are all use uh default values. So we are not going to do normalization. So actually nothing need to be sent in, right? And output embedding. And we can show the output embedding dot shape. We can guess that uh, according to our assumption that the output shape should be yeah, I think I need to send in the batch size, right? And the output shape should be 1 and yes. Now we are going to run this program to see if our prediction is right or not. Now wait a few seconds. Yes, it's exactly the same as the thing our prediction. So yes, that's all about patch embedding. I highly recommend you to read this paper, which is the first successful uh, attempt to use transformer to um, do task in computer vision directly. So I'm going to post the link to the paper in the description. And thanks for watching my video. And if you have any question, you can write them in the question. I will answer them as soon as I saw your question. And thanks for watching. If you are interested in implementing vision transformer, you can subscribe my channel, and uh, I will implement other things in the next videos. That's all. Thank you.